Okay, hi. My name is Gabe Sosa Castillo, and I'm very honored and privileged to be giving a talk for the Café con Leche initiative from Lathisms. And so it's wonderful to be here, and I hope that you enjoy the video where I talk about descriptions of the defining equations of certain families of toric ideals, which is a main area of research that I work on. So let's tell you a little bit about what I'm going to talk about. So we'll spend some time discussing what I find fascinating about mathematics. I think it's important for these kind of initiatives to always talk a little bit about what the person who is giving the talk finds so exciting about math. And then I'll go and give some definitions, especially for toric rings, which is the main object that I'm going to be studying. And then I'll do a quick discussion about monomial orders and Grobner bases and why do we care about them. And then we'll talk about monomial orders and monomial ideals, especially a strongly stable property, which is the type of toric rings that I have worked on the most. And then I'll give you a history of developments in that area. And then I will discuss mainly the new results that I have contributed to in the last 4 years. Okay, great. So here we go. So what do I find fascinating about mathematics? That's an excellent question. And so I'm going to say the two things that in this talk in particular are the bones, the skeleton of what I like about math. So the first of these things is that when you do math, sometimes this very peculiar thing happens when you can take a problem or a concept in a certain branch of mathematics, and then you are either going to solve it or interpret that concept using methods or techniques in a completely different branch of mathematics. So that's, in my opinion, fascinating. I don't think that there are many places where you can do this. So an example, the classical example of this is the fundamental theorem of algebra, because the proof doesn't really involve algebraic methods. It's a proof that is from complex analysis. Another example, when we do a translation between concepts of different areas, is the algebra geometry dictionary, where you do an interplay between an ideal, which is an algebraic object, and a variety, which is a geometric object. And so the whole goal is to understand varieties via their ideals, or sometimes we want to understand properties of the ideal because we know what geometrically the variety satisfies. So again, it's fascinating, this interplay of translating from one to the other. And we're going to do that in this talk, but with combinatorics mostly. So the second thing that I find really fascinating about math is that you can take a problem in a certain branch of mathematics, and sometimes it's impossible to solve it. But what you can do is approximate the solution. You can transform whatever object you're working with an object that you understand better. And then whatever thing you were trying to say about the original object is somehow close to the properties to the objects that you're using for the approximation. So an example of this is the Stone-Weierstrass theorem, which is you can express a continuous function as a limit of polynomials. And of course, again, polynomials is something that we understand really well analytically. So then, a continuous function, no matter how weird it is, there's a way of playing this game. Okay, so that's again kind of what we're gonna do. So let me show you a little bit of where this interplay is gonna come. And the whole point is, in this case, the property truly comes from monomials. So what is a monomial? So a monomial in variables, and the variables are x1, x2, up to xn, is an expression that is a product of these variables. So it's x1 to the alpha 1 times x2 to the alpha 2 times xn to the alpha n. And the alpha 1, alpha 2, alpha n's are non-negative integers that are telling you how many times you are multiplying by the variable for which the alpha I is an exponent for. So for example, we can do x1 cubed times x squared times x3 to the 4. And this is a monomial in 3 variables. It's also a monomial in 4 variables if we understand that if we don't write the x4 is because we have an x4 to the 0. So technically, what I should say is that this is a monomial in 3 or more variables. Okay, so that's what a monomial is, and it's going to be the main object that we're going to use to do these, what I find fascinating about mathematics part 1, which is we're going to do a combinatorics idea attached to an algebra idea. Okay, so what's the point of monomials? So we want to work on polynomial rings. Polynomial rings are a very fundamental object in abstract algebra. So what is a polynomial ring? So essentially you need to have first a ring, and we're gonna call that ring R. And then we're gonna consider n variables over that ring, in a sense that what we're gonna do is we're gonna find all possible finite sums of products of elements in R and monomials in the n variables. So an example is if I give you P1, which is a polynomial, as x1 squared, that is a monomial, minus 3, that is an element of the integers, times the monomial x1, x2, x3, plus 5, and that is an integer, times x2 cubed, x3 squared, which is, again, a monomial. So in this is a finite sum of products of elements in the integers and monomials in 3 variables. So this is a polynomial over the polynomial ring in 3 variables over the integers. Throughout this talk, actually, the ring will be an algebraically closed field K of characteristic 0. This is not going to matter a lot at the beginning, but when we get to like the actual result that I have contributed to, this is key that we work on algebraically closed fields with characteristic 0. Well, the perfect example for this is just the complex numbers. Okay, so one of the main objects in algebra when we talk about polynomial rings or rings in general is the concept of ideal. So an ideal is generated by certain elements over the ring. Turns out that what we want to do in this case is, because we're working on a polynomial ring in variables, what we're going to do is we're going to consider some polynomials. And in this case, I wrote a finite number of them. And I do this because when we're working over a polynomial ring in variables over a field that is algebraically closed and has characteristic 0, actually, there's a result by Hilbert, the Hilbert basis theorem, that tells us you could have way more polynomials, an infinite amount, to generate an ideal, which is what I'm about to describe, but you can always find, in the case when the ring is Noetherian, a subset of that collection of infinite polynomials that is finite and generates the same ideal. So what is an ideal? An ideal is, well, you have these polynomials, which we call the polynomial generators, f1 through fs. And what you're going to do is you're going to consider all possible combinations of products of polynomials in the polynomial ring and the polynomial generators. So, for example, in the case where I have that f1 is x cubed y, x cubed minus xy, and f2 is xy squared minus y, then f, which I'm going to say is y squared times x cubed minus xy, plus negative x squared times xy squared minus y. So this is h1, this is f1, this is h2, and this is f2. And so this is x cubed y squared minus xy cubed minus x cubed y squared plus x squared y. And this gives us x squared y minus xy cubed. So f is an element of the ideal generated by f1 and f2. So again, that ideal consists of all polynomials that can be written as the product of a polynomial h1 and f1, which is one of the polynomial generators, and adding a product of another polynomial h2 and another polynomial generator f2. Okay, great. So let's play a little bit with an introduction for how monomials create these connections and how ideals create these connections between different branches of mathematics and algebra. So we can consider an example of a square-free monomial ideal. So in this case, let's say that this ideal is the ideal generated by x1 x cubed, comma x1 x4. So again, I delta is everything that can be expressed as f times x1 x3 plus g times x1 x4. So this is a square-free monomial ideal. Turns out that there is an extremely cool interpretation of the quotient ring of the polynomial ring in 4 variables when you mod out by that ideal, because this is closely related to working with a simplicial complex. So here we have a simplicial complex, and what happens is that x1, x3, and x1, x4 are the minimal non-faces of this simplicial complex. So when we have this kind of object, this actually is called a phase ideal. And this that we have here is the Stanley-Reisner. So that's not going to be the point of the talk, but I'm again just showing you that there is a way to understand a square-free monomial ideals in terms of simplicial complexes, which are more of a topological object. Okay, so we have another example where we're talking about the ideal x squared plus y squared plus c squared minus 1 generated by that polynomial and 2x plus 3y minus 2c, which is also a polynomial. So in this case, what we're doing is this is an ideal. This object is an ideal generated by 2 polynomials, but geometrically, it's actually a variety. It's a variety by the intersection of the sphere, because if I make this equal to 0, that is the equation of the sphere centered at the origin that has radius 1. And if I look at 2x plus 3y minus 2c, and I make that equals to 0, that is the equation of a plane through the origin that is normal to the vector 2, 3, negative 2. So this ideal, which is, again, an algebraic object, corresponds to a geometric object, which in this case is a variety, as I had mentioned previously. Okay, great. Let's do a third example. So this time we have an edge ring. So what is an edge ring? An edge ring is a subring of a polynomial ring, where instead of having the variables x1, x2, x3, what you're trying to do is you're trying to see all of the things that are generated by a specific set of monomials in the same way that a polynomial ring is built. So this is a specific type of subring. And because these generators are all square-free, turns out that there's a way to interpret this as a graph. And here it is. So how am I interpreting this edge ring as a graph? Well, it's very simple. What we're doing is there are actually 4 variables involved here. So we're going to create a vertex for each one of the variables. So we have a vertex for x1, a vertex for x2, a vertex for x3, and a vertex for x4. And now what we do is we look at, okay, x1, x2 is one of these monomial generators for the subring. So that means that I better create the edge that connects the vertex x1 and the vertex x2. I have x2, x3 as another one of these square-free monomials that generate this edge ring. So I'm going to create the edge x2, x3, and I'm going to do the same for each one of the monomials that we have. And then we get x2, x4, which is our big winner. And that's the graph that we get. Yay! So we have made a connection between a graph theoretical object, which in this case is a graph, and an algebraic object, which is, in this case, an edge ring. Okay, so let's talk about toric rings, because that is the main object that I study. This is what I play with all the time. So in this case, this definition is not going to be the typical definition of a toric ring, because I want to give it in terms of collections of monomial ideals, because it connects to the other aspect of the things that I do research on, which are Rees and multi-Rees algebras. But I don't want to go too deep into the concept of what a Rees and multi-Rees algebra. What I'm going to say is that they involve objects that are associated to these types of toric rings that I'm about to describe. So let's just focus on what this type of toric ring is. So the definition is we have I1, I2, IR, which is going to be a collection of monomial ideals. So what this means is that this ideal, I1, is generated by a certain set of monomials. I2 is generated by another set of monomials, and IR is generated by another set of monomials. So what I'm trying to say here is that I take I1, and there are some monomials that generated. So let's say that there are S1 of them. And so I'm just going to call them U11, U12, up to U1S1. That way, I know that those are the monomials that are coming from the first ideal. And then I'm going to say I2 is another monomial ideal. So it's going to be generated by U21, U22, up to U2S2, where S2 again is the number of minimal monomial generators of I2. And we keep doing this until I get to IR, which is then generated by SR of these monomials. And so they're going to be called, you guessed it, U11, UR1, UR2, and so on up until URSR. So the associated ring, the toric ring associated to the module I1 direct sum with IR. So this is the module that we are studying in this particular case, is the subring of the polynomial ring in n plus r variables. So n is number of variables in the polynomial ring where I1 all the way to IR live, and R is the number of ideals that we are considering. So what we're doing is we are then creating a new subring from this polynomial ring in n plus r variables, where we take the monomial generators of the first ideal and we multiply them by T1. Why are we multiplying them by T1? To keep track that they are monomial generators of the first ideal. And then we take the monomial generators of the second ideal and we multiply them by T2. Why are we doing this? Because it might be that ideal 1 and ideal 2 have a common monomial generator. So we have to be able to distinguish the fact that, oh, that common monomial generator is the one from the first ideal instead of the one from the second ideal. So the T's are just keeping track of this. And then we do the same with our final ideal IR. We take the monomial generators of that ideal and multiply them by TR. So this toric ring associated to this module is usually written as f of that direct sum of ideals, that module. So the reason that we, again, are interested in this is because this is a multi-fiber of a multi-Rees algebra. That's the idea behind. So if you are watching this video, you're an algebraist, then yeah, you're getting what the point of this is in a larger picture. But again, my intention is to invite general mathematicians to understand the basic ideas of Toric rings and how we study them. So the thing is, to study this type of Toric rings, we can construct what we call a presentation of the Toric ring itself. So how do we do this? Well, it's very simple. We're going to take S, which is the polynomial ideal involving the n variables, where the polynomial ring involving n variables, where these ideals live. And we're going to denote the exponent vector corresponding to the monomial uij by alpha ij. So what I mean by a monomial vector is if I have x1 cubed, x3, x4 squared, then the monomial vector corresponding to this is 3, 0, 1, 2. That's the exponent vector of this monomial. So we're going to find the exponent vector for each one of the monomial generators of our ideals. And what we're going to do is we're going to create a new polynomial ring where we're going to create a variable for each one of these exponent vectors. So that means that we're actually effectively creating a t variable for each one of the monomial generators that we have for the ideals that were given to us. So we're going to take this polynomial ring in the t variables, and we're going to create a surjection into the polynomial ring. Remember, S is the polynomial ring in n variables, where we also adjoined the r variables that are keeping track of what ideal we are working on. And what this map is going to do is it's going to take the variable, the t variable corresponding to exponent vector, and it's going to send it to the monomial that has that exponent vector multiplied by ti. So that we know that, again, this is a monomial generator of the ith ideal. And we're going to extend this algebraically. So what I'm trying to say is, imagine that I have T1, 0, 2 times T 2, 1, 1. And again, 1, 0, 2 happens to be alpha 1, 1. And 2, 1, 1 happens to be alpha 2, 3. So we have this. Let's say that I have 3 times this plus 2 times t of 1, 0, 3, and this is alpha 3, 1. That's 1, 0, 3. So if we do the image of this polynomial in the t variables using our map phi, what we obtain is 3 times, and this is then x1 times x3 squared, because that is the exponent vector for that monomial, times t1, and the reason that it's t1 is because 1, 0, 2 was alpha 1, 1, times, and now 2, 1, 1 is alpha 2, 3, so it's going to be x1 squared, x2, x3 times t2, plus 2 times, and then we're going to take T103, which we know is alpha 3, 1. So that means that it's coming from the third ideal. And the exponent vector is x1, x3 cubed. Okay, so that's what we're doing. That's what we mean when we say that we are extending this mapping algebraically. Okay, so we have created a surjection. The amazing thing about this is that the first isomorphism theorem of ring theory tells you that then the image of this map, because the map is surjection, the map is not a surjection. The map is a surjection to our Toric ring. So the image of this is surjective to our Toric ring. So it happens to be that it is the quotient of our starting polynomial ring by the kernel of that map. And so now we are able to understand better. So now this is, again, what I find fascinating about math part 2 is, instead of working with this subring, which is a little bit complicated to visualize or even understand, now we are able to express this as a quotient ring of a polynomial ring, which is a very well understood object, and an ideal, which happens to be the kernel of the map that we created, the surjection of this polynomial ring into the toric ring that we wanted to study. Okay. So the ideal I, which is the kernel of this map, this ideal is called the defining ideal of the toric ring associated to the module that we're studying. And the minimal polynomial generators of that ideal are called the defining equations of that toric ring. So again, remember, the name of this talk is describing the defining equations of toric rings. So I have laid all the groundwork for now comes to the description. The whole point of this is I want you to know that there is a way to describe the generators of this ideal by exploiting some type of combinatorial, either object, combinatorial invariant, or if there's something that is going to help us understand this ideal better. Okay, great. So let's revisit the connection between graphs and monomials. So remember, what I mentioned before is, okay, so I have a graph. My graph is a graph on 6 vertices in this case. And what I'm going to do is I'm going to give a variable to each one of the vertices, x1, x2, x3, x4, x5, x6. Okay, so that means that this can somehow be understood as a subring of a polynomial ring in 6 variables. And in fact, we say that the H ideal is the ideal generated by the products of variables corresponding to vertices joined by an edge. So in this case, the H ideal is the ideal generated by x1, x2, that is one of the edges, then x2, x3, which is the next edge, x3, x4, which is the next edge, x4, x5, which is the next edge, x5, x6, x6, x1, and x1, x4. So this is the H ideal of this graph. So, and we have a toric ring associated to this H ideal. So that toric ring, again, is the polynomial subring, the subring of the polynomial ring where we are considering the monomials that live inside of this H ideal. So because of what I told you before, there is a way to create a new polynomial ring where we're going to do a surjection into this subring. So that polynomial ring is going to be T12, T23, T34, T45, T56, T16, and T14. So essentially what I'm doing is I have created, some people might not want to do that. They might just call it H1, H2, H3, H4, H5, H6, and H7, and make, that's H2, H1, H2, H3, H4, H5, H6, and H7. So we create that, and then what we're saying is our function is going to go into this toric ring, and what we want to say is that phi of EI, it's the corresponding, phi of E1 is x1, x2, phi of E2 is x2, x3. So you are sending an edge to the product of the variables corresponding to the vertices that define that edge. Okay, great. So it turns out that in 1995, Villarreal published a paper where he gave a description of what the defining ideal of the toric ring associated to an H ideal of a graph should look like. And it turns out that he said that the defining ideal of the toric ring associated to an H ideal is generated by the binomials defined by the alternating steps of even closed walks in the graph. What do we mean by this? So an example of a closed walk in this graph is E1, E2, E3, E4, E5, and E6. This is an even closed walk. Why? Because if we start here and we do this, we got back to our starting position. That's why it's closed, and it's even because it took an even amount of edges to do this. So what happens is that according to Villarreal, based on this, the ideal that describes this, one of the generators of this ideal, so maybe I'm going to say just one of the generators of this ideal. So one of the generators of the ideal that we're studying is related to the closed even walk E1, E2, E3, E4, E5, E6. And how do we do this? Well, it turns out that it is E1 times E3 times E5, because those are the odd steps. That's what we mean by alternating. And then we subtract E2, E4, E6, which in this case are the even steps. So that binomial who lives in this binomial lives in the polynomial ring that we created to have a surjection into the toric ring that we were studying. So in fact, if we wanted to find all of the monomial generators in this situation, they would be, okay, so let's look at the even closed walks that are minimal. So we have E1, E2, E3, E4, E5, E6. That is this even closed walk. Then we also have this even closed walk, E1, E2, E3, E7. And we have this even closed walk, which is E7, E4, E5, E6. So this closed walk, if we take the odd steps and subtract the even steps, gives us E2, E4, E1, E3, E5 minus E2, E4, E6. Then here, if we do the same and we take the odd steps and subtract the even steps, then we obtain E1, E3 minus E2, E7. And then here we can do E7, E5 and subtract E4, E6. So if we take these three binomials, we actually have the defining equations for this ideal. And this is all thanks to that result by Villarreal from 1995. Okay, great. So that's a way of study toric rings associated to graphs, which is not the main thing that I do, but I have done a little bit of work on these kinds of things. So let's talk about monomial orders and Grobner bases, which is really what focuses the type of research that I do, because my desire is to determine defining equations that actually form a Grobner basis. But to tell you why I care about that, first I need to tell you what a Grobner basis is. Okay, so let's go back to monomials. Remember, monomials are just products of variables, and we can look at them as exponent vectors. So a monomial order is a total order on the set of monomials of a polynomial ring that satisfies two additional properties. The first one is one better be the smallest monomial according to the monomial order. And the second property is a monomial is less than another monomial according to the monomial order, then if you multiply both monomials by the same monomial, then the order should be preserved. So these are reasonable properties that we want to have. Turns out that a lot of computer algebra systems currently, things like Macaulay 2, Cocoa, Singular, even Julia, and things like this, they all use prescribed monomial orders. There are three that are the main ones that are used because they're very useful, and one of them makes computations particularly fast, and the other ones have properties that when you compute things using those monomial orders are desirable. So let's spend a little bit of time discussing these three main orders that exist for monomial orders. One of them is called the lexicographic order. So how does the lexicographic order works? Say that you have two monomials, and one is x1 to the alpha 1 times x2 to the alpha 2 times xn to the alpha n, and you have a second monomial m2, which is x1 to the beta 1 times x2 to the beta 2 times xn to the beta n. And what you really want to do is compare these two monomials. You want to know, okay, so which one is the biggest one? And so essentially what you do is you look at the corresponding exponents until you find corresponding exponents that are not the same. So if alpha 1 is equal to beta 1, move on to alpha 2 and beta 2 until you find two that are not the same. And then what happens is that the one that has the highest exponent, the first time that the exponents are not the same, is the one that is higher according to the lexicographic order. Okay, and it's called lexicographic because if we wrote variables starting with the letter A, this would mean that the monomial that is higher appears first in the dictionary, hence the name. The second monomial order is called what the degree lexicographic order. Some people call it the graded lexicographic order. And so what you do is first you complete the total degree of both monomials. If the total degree of one of the monomials is higher than the other one, then that is the one that is higher according to the degree or graded lexicographic order. If the total orders are the same, then there's a tie in terms of total degree, but you break that tie by going back to the lexicographic order. Okay? And then the third order, which is the most useful computationally speaking, because again, is the one that is fastest, is the reverse lexicographic order. So the reverse lexicographic order is a graded order. So maybe I should have written the graded reverse or the degree reverse. But the reason that I didn't do this is because the reverse lexicographic order itself, if you don't do total degree first, it's not a monomial order. So there's no reason to study it in that sense. So the reverse lexicographic order, what you want to do is, again, compute total orders first, and then the one with the highest total order is the one that wins. Or if the total degrees are the same, so if there's a tie, what we're gonna do, and this is one of the reasons why it's called reverse, is we're gonna start at the end, beta n compared to alpha n, and trying to see at which moment they are not equal. So starting from the end, we start moving to the left until we see two corresponding exponents that are not equal. And then the one that has the largest exponent is the one that is lower according to the reverse lexicographic order. So the reverse lexicographic order, in a way, behaves reverse in terms of lex in two different ways. The first one is, instead of comparing things starting from 1 and then going to 2, is you start at the end. So you start at n and then move to n minus 1. So it's reverse. And on the other hand, the moment that there's a tie that is broken, that there are two exponents that are not the same, the lexicographic order has the one with the highest exponent be higher, but the reverse lexicographic order has the one with the highest exponent be lower. So it's reverse in two aspects. Okay. So let's talk about what a leading term of a polynomial is. So if we have a monomial order and a polynomial that is not zero, And in a polynomial ring in m variables, we say that the leading or initial term of that polynomial, and we denote that in f, is the largest monomial appearing in the canonical expression of f with respect to the monomial order. So let me give you a couple of examples that we're going to use in a second. So if we have f is x cubed minus xy, then in lex of f is x cubed. Because x cubed, how many, if you look at this as an exponent vector, this is 3, 0, while this is 1, 1. So if we look at exponents one at a time, starting with x, again, lexicographically, x has the highest exponent. Now, if I have, say, g, and g is xy squared minus y, then in lex of g is xy squared. Why? Because, again, this is 1, 2, and this is 0, 1. So the exponent for the x for xy squared is higher than the exponent for the x in y, which is 0. And let's do a third one. So if we have h, which is x squared y minus xy cubed, then in lex of h is x squared y, because this is 2, 1, and this is 1, 3. But if we had done in of dec lex, the degree lexicographic of h, then it would have been xy cubed, because the total degree of xy cubed is 4, while the total degree of x squared y is 3. And remember, if we're talking about degree lexicographic, then the one that matters first is who has the biggest total degree. Okay, excellent. So we can now define something that is called the initial ideal. So given a monomial order, what we do is we say that the initial ideal of a given ideal with respect to that monomial order is the ideal generated by the leading monomials of all polynomials in I. Okay, so let's do a fun example. So if we have I generated by x cubed minus xy and xy squared minus y. So this is generated by what I previously called f and g. You might think that the initial ideal, according to lex of I, is x cubed and xy squared, because those are what we declared before to be the initial things. Unfortunately, that is not true. I can show you why it's not true very simply, because h, who we have as h before, who is x squared y minus xy cubed, earlier in the talk, we said is y squared f minus x squared g. And in lex of h, we said was x squared y. And as you can see, x squared y is neither divisible by x cubed nor by xy squared. So that means that, again, in lex, the initial ideal with respect to the square root of I should include x squared y, because that is the leading monomial of one of the monomials in I. But that is not the case if these were the initial. So that means that this is not the initial. So now we have that crazy part of, oh no, it's not enough to just do the initials of the generators to find the initial ideal. This is where the concept of Grobner basis comes in. So given a monomial order over a polynomial ring and an ideal in that ring, we say that a set of generators of the ideal is a Grobner basis if it generates the ideal, and it also, the initial terms of those generators generate the initial ideal. So a Grobner basis is essentially something that pulls double duty. Is on one hand, it's telling you that the generators really generate the ideal, but it's telling you also that the initial terms of those generators generate the initial ideal. And so remember that I told you that the other thing that I find fascinating about mathematics is when we approximate things. So it turns out that in algebra, sometimes to understand an ideal, instead of understanding the ideal, it's easier to understand a monomial ideal that is associated to that ideal. And the perfect candidate is the initial ideal for the ideal that we have. So that's why monomials are central. We're able to describe certain algebraic properties of a general ideal, which is not generated by monomials, using instead ideals that are generated by monomials. And monomials are easy to understand in a sense, because you can actually play games with them visually, or you can play games with them combinatorically. And okay, so let's revisit the definition of a monomial. So a monomial in n variables is an expression of the form, again, a product of variables, but we can write this as a vector. And the great thing about writing monomials as vectors is that it gives us, again, this interplay between something that is extremely visual that allows us to understand properties of the monomial ideal. So, for example, if we take the monomial ideal x cubed y, y cubed, xy squared, and I look at x cubed y, so that corresponds to the point 3,1, and y cubed, that's the point 0,3, and xy squared is the point 1,2, then I can select every point in this lattice that is directly above or to the right or above and to the right. So essentially, it's as if I was moving the origin to be placed here, and I select everything that falls either on the first quadrant or on that border from y cubed. I can do the same with xy squared, and I can do the same with x cubed y. So see, I have gotten all those blue dots. It turns out that all those monomials that were selected form a vector, a k-vector space for the polynomials that live inside that monomial. And if instead I look at the quotient ring where I mod by that monomial ideal, the polynomial ring into variables, the red dots, the ones that don't fall into the region that I created before, but are on the first quadrant, those are a k-vector basis for that quotient. So like I said, the whole thing is monomials give you this visualization, and they also play combinatorial games. This is the strongly stable property. That's something that I study. So a strongly stable property tells you that if you have a monomial ideal, this monomial ideal is what we call strongly stable if whenever you take a monomial in the ideal and there's a variable that divides that monomial, then you can effectively replace that variable by a variable that has a smaller subindex. So by a variable that increases in the lexicographic order. So let's look at the example of the ideal that I gave you before, y cubed, xy squared, and x cubed y. That ideal is not strongly stable because xy squared is divisible by y. So I can replace the y by an x and get x squared y. And as you can see, x squared y, which is this monomial, is not part of the ideal. So this is not a strongly stable ideal. But this one, y cubed xy y squared, which I have here, is actually strongly stable. There's a very easy visual way of knowing if something is strongly stable. If you take y cubed and you come southeast, and everything is on the ideal, then that ideal is strongly stable. You can make these kinds of diagrams for monomial ideals in two variables. You can represent them in R2. But if you have monomial ideals in three variables, then you can represent them visually in R3 and in four variables R4. But then again, that now it becomes really complicated because visualizing something in R4 is just as difficult as not working like that. Now, this is the other thing. Sometimes instead of actually focusing on the number of variables, you can focus on the degree of the monomials that you're working with. So if you have monomials that are all of degree 2, you can also create a visual representation in R2. But this time is because we're working with the degree being 2. So x1 squared is here because you're essentially saying, well, this is 1, this is 2, this is 3, this is 1, this is 2, this is 3, this is 4, this is 5. And so you can get x1, x5, x1, x4, x2, x4, x3, x4. So things of degree 2 can also be represented in a certain way in R2, which means that also things of degree 3 can be represented in R3. These, the monomial ideal generated by these monomials that I have here is strongly stable. How do I know that? Is because, again, I can do what I call a Borel reduction. So I can take x1, x5, for example, and replace the x5 by x4, and I get x1, x4. Or I can take x3, x4, and I can replace the 3 by a 2 to get x2, x4, or I can take x3, x4 and replace both the 4 and the 3 by 2s, and I get x2 squared. So that is, again, a combinatorial. There are combinatorial properties for strongly stable ideals, which is why they are desirable, and that's why we study them. So to be able to describe a strongly stable ideal, because everything can be obtained just from some of the monomials via those things that I call a Borel reduction, then that means that to understand the strongly stable ideal generated by these 4 monomials, I don't need all 4 of them. I only need x1, x2 cubed, because I can obtain the other 3 monomials from this one by playing this exchange game. Or if I have this monomial ideal generated by these 10 monomials, I don't need all 10. I know that it's strongly stable. So all that I really need is x1, x5, and x3, x4, and I can obtain all the other ones via Borel moves. So this type of strongly stable ideal is called principal because everything can be obtained from one monomial. This monomial ideal, which is strongly stable, we call it 2 strongly stable generated or 2 Borel generated because it requires 2 monomials to find all the rest. Okay, so now is when I actually get to talk about the kind of research that I do and why is this so important and why did we do all this craziness. And so what's happening is that there are these 3 very fundamental theorems, foundational theorems that I'm about to tell you that actually tell us, people who do algebra, that if we are able to find certain properties of the generators of the defining equations, the defining ideal, if we are able to say things about these generators, then we're actually able to say things about the toric ring. So the first result is by Hochster from 1972, and it says that if a toric ring generated by monomials is normal, then it is also Cohen-Macaulay. So again, like, what do these properties mean? I'm out of time to tell you in depth what they mean, but I'm telling you that these are properties that algebraists really care about. The second theorem is by Sternfels, and it says that if there is a Grobner basis for the defining ideal of a toric ring generated by monomials, such that the leading or the initial terms of the generators of this defining ideal are all square free, so that means that they are not x squared, for example. They are powers, or there are no powers involved. They are products of just variables that are never repeated. Then if that happens, the toric ring is normal. And so knowing what Hochster said, that if it's normal, it's also Cohen-Macaulay, you're getting 2 properties, 2 algebraic properties that you want for the price of 1. All you need to do is find a Grobner basis for that defining ideal with the property that the generators have leading terms that are square free. And the third theorem is a theorem due to Froberg from 1999, which tells us that if there is a Grobner basis for the defined ideal of a toric ring generated by monomials, such that the leading initial terms for the generators of its defined ideal are all of degree at most 2, then the toric ring is a Koszul algebra. And Koszulness is a property that as an algebraic, we really put a premium on certain things because it's something that gives us bounds on another algebraic property that is called regularity. So essentially, the takeaway from these three theorems is if you're able to find a Grobner basis for the defining ideal of a toric ring, and the leading terms of that are square free and are all of degree at most 2, then your toric ring is a Koszul algebra, is Cohen-Macaulay, and is normal, which again, they are all desirable properties. So now I'm going to tell you a quick history of the research that has been done on Riesz algebras and multi-Riesz algebras, but I'm going to start with Riesz algebras. So this starts in 1999 with De Negri, in a sense, where she discovered that the special fiber ring, which is the toric ring, of a principal strongly stable, so this means that, again, this is a monomial ideal with the strongly stable property where you can get all of the generators of the monomial ideal by just using one of them via these exchanges that I described recently. So if you have the special fiber of a principal strongly stable ideal that is a very specific type of toric ring, then that toric ring is Koszul, Cohen-Macaulay, and normal. So obviously what De Negri did is she used some kind of arrangement, and I have one example behind me in this board. She used an arrangement to describe a combinatorial invariant that allow her to say, this is a toric, this is the Grobner basis. This Grobner basis with respect to a certain monomial order, this is the Grobner basis for the toric ideal. These are the defining equations, and those defining equations, as I mentioned before, happen to be a square free and of degree at most 2 on the leading terms, so you get all the 3 properties. In that same paper, De Negri actually said that the special fiber ring of a Lex segment ideal is another type of a strongly stable ideal, but the number of generators that you need in the strongly stable sense can be as high as you want, because what a Lex segment ideal is, you take all of the monomials using the lexicographic order, starting from x1 to the d, so you fix a degree, and you take all of the monomials decreasing using the up to 1 monomial that you choose. So a Lex segment ideal is an example of a strongly stable ideal. So again, De Negri used this trick that I have behind me, and with that, she was able to describe a Grobner basis with respect to a certain monomial order for the defined ideal that had leading terms square free and quadratic of degree at most 2. So immediately we get that it's Koszul, Cohen-Macaulay, and normal. So fast forward a few years, and in 2005, Herzog, Hebe, and Bladoiu then proved that the Riesz algebra, again, these are special fibers, they're not Riesz algebras, they are certain types of toric rings, but a Riesz algebra has a special fiber attached to it. And so what Herzog, Hebe, and Bladoiu did is they said that if the Riesz algebra of a strongly stable ideal is of fiber type, what that means is that you can find a Grobner basis for the Riesz algebra, for the defined ideal of the Riesz algebra, by adding linear CCGs to the Grobner basis of the defining ideal of the special fiber. So because of De Negri's result, put together with Herzog, Hebe, and Bladoiu, immediately you know that the Riesz algebra of a strongly stable ideal is indeed Koszul, normal, and Cohen-Macaulay. So you get, again, all 3 properties that I said we put a premium on just in one thing. So in 2004, so before the paper by Herzog, Hebe, and Bladoiu, Conca and De Negri actually found an example using a defining ideal of the special fiber ring for the strongly stable ideal with these Borel generators, and it has a minimal cubic generator. So if there's a cubic binomial generator, that means that you cannot find a Grobner basis that has things of degree at most 2. So that means that this is an example of a toric ring that is not going to be Koszul. So then, of course, the natural question is, well, this is what happens when you have 3 strongly stable generators for the ideal. So the question is, what happens with 2? So this question was open back from 2004, and I worked with Michael Di Pasquale and Chris Francisco, Jeff Mermin, and Jay Shrake, And in 2018, we actually proved that there is algebra of a strongly stable ideal with two Borel generators, so two monomials that generate everything strongly stable. All of the other generators, by using this exchange property that I mentioned, is actually Kosul. It is not normal in general, though. And computational evidence tell us that it looks like it's Cohen-Macaulay, but we haven't found a proof for that. So the one property that we were able to truly extract was the Kosul property for when you have two generators. So let's move on to the history of the results that were obtained now when you switch from a Riesz algebra to a multi-Riesz algebra. So the case of the multi-Riesz algebra is where we use that construction that I mentioned before, where I'm taking several ideals, several monomial ideals, and I'm doing the direct sum of them. So I have to keep track of what ideal is giving me what monomials. So this starts in 2013 when Lin and Pollini proved that the multi-Riesz algebra and its associated special fiber of the direct sum of powers of the maximal ideal of a polynomial ring is Kosul and normal. And of course, then it's Cohen-Macaulay. But that was the main result of my thesis in 2014, is a generalization of their result. Because what I realized is that actually it's not the fact that they are powers of the maximal ideal. What is happening is that they are principal strongly stable. So it means that every one of the ideals can be obtained via this exchange property from one specific monomial. So the proof of my result is that the multi-Riesz algebra and associated special fiber of the direct sum of principal strongly stable ideals satisfying an ordering condition. So it's not any direct sum of principals. There has to be something about these specific monomials that generate each one of the ideals in the Borel sense. They need to satisfy an ordering condition to be able to guarantee that it's Kosul, normal, like Cohen-Macaulay. So then in 2020, Michael Di Pasquale, who again was one of my co-authors in the 2018 paper, and Jabbar Neshat, proved in 2020 that in fact, you don't even need the ordering condition. It's the multi-Riesz algebra and associated special fiber. It's always Kosul, normal, and Cohen-Macaulay. You don't need those special generators in the strongly stable sense to satisfy this ordering condition. So now we move on to the recent results that came after that. But again, like I want to then stress the fact that my main results and my main papers up to 2020 had been about the Kosul property for the most part, or things about properties of monomial orders, or whether certain strongly stable toric rings have defining equations using this combinatorial invariance. So in 2022, there's this paper that I co-wrote with Selby Cara and Quainoan Lin, where we actually decided to start thinking, well, what happens if we study multi-Riesz algebras of strongly stable ideals, but instead of thinking about them being principal, we try to see what happens if we instead think of how many generators does each ideal have, and what is the degree of each one of the generators. So of course, we already know that these ideals cannot have 3 generators or more, because then that example from Conca and Denegri tells us that there's a possibility that it's not going to be Kosul. And what we want to do is find a description for the ones that are Kosul in terms of certain parameters. So the first main theorem of that paper is we extended the result of Herzog, Hivy, and Bladoiu. We said that the multi-Riesz algebra, the direct sum of strongly stable ideals, is also of fiber type. So that means that if we're able to understand the multi-fiber, we know what the defining equations of the multi-Riesz algebra are. And that's the result that I have here. That's the description of the Grobner basis. So the idea for the proof is we use the concept of a directed graph. So again, what we're doing is this is where the combinatorics comes. We create a directed graph using monomials and exchange properties. And so this is a modification of a concept introduced by Sternfels, which is called the fiber graph of a monomial for toric rings. And then we use a counting technique to define an invariant. So again, this is extremely combinatorial. In the proof is extremely combinatorial. It's about keeping track of invariants and seeing how we're moving around a directed graph. The second main result of that paper is the one where we actually were able to discuss when is it possible that the whole family of multi-rings of strongly stable ideals is Kosul, normal, and Cohen-Macaulay, or at least Kosul, if we know information about how many generators in the strongly stable sense each one of the ideals have, and what are the degrees of the generators and how many ideals we have. So what we said is if we have a certain number of generators for each one of the ideal, and we have the degrees, and the degrees are in increasing order, then the multi-ring algebra is Kosul for any collection of strongly stable ideals. Then one of the following must be true. Either you have exactly two ideals, and both of them have two generators, and the degrees of those generators are either 2 or 3. Also, we can have more than 2 ideals, but in that case, the first R minus 2 of them are principal. The last 2 are 2 generated in the strongly stable sense, and the degrees of those that are 2 generated are 2 or 3. Or we have a situation where you have more than 2 ideals, or 2, and the first R minus 1 of them are principal, and the last one is either principal or at most 2 generated. So these are the only cases where you could have a theorem about the family being Kosul. And then the third main result of that is that indeed, in the case where we have exactly 2 ideals, both of them strongly stable, both of them with exactly 2 Borel generators, and both of the generators of degree 2, then in that particular case, the multi-fiber, which is a toric ring, possesses a Grobner basis of quadrics. So we obtain that the special fiber is Kosul, and that means that the multi-ring algebra is Kosul. And so I just want to show you the kind of structure that we play with. So essentially what we do is we take the first ideal, and we declare that we're going to order the ideals in a way that the second ideal is the one that has the smallest Borel generator with respect to the reverse lexicographic order. So then we create like kind of a floor plan. Imagine that this is a 2-story house. The first floor is for the first ideal, and the second floor is for the second ideal. And what we do is we move along the first floor in the way that these red arrows are showing us. We write those variables, the t variables corresponding to these monomials, we write them in that order, and then we move to the second ideal, coming above the biggest of the generators. And so we traverse again using this kind of a snake pattern, that part, and then we go back to the beginning, and then again we traverse that snake pattern until we finish here. So if we organize the variables for the t's following this structure, and then we use the reverse lexicographic order, that gives us a Grobner basis of quadrics for the defining ideal of this special fiber. So again, that's what happens. There's another way of understanding this if you're an algebraist. So what happens is you can instead think of this again as a floor plan. And again, this is the first floor and this is the second floor. And if you look at this as a 2-story special house, then what you can do instead is select, 2 rooms. They could even be in different floors. And then you can create a 2x2 matrix by taking the rectangular arrangement for them. And if you compute the determinant of all of those 2x2 minors, selecting any of these things, then that is also a description of the defining equations for the ideal of this toric ring associated to this multi-Rees fiber. So it's exciting because now we're seeing it from all determinantal ideals, like looking at minors, or we can see it as this construction following the this snake kind of move, but they coincide. So that's the big thing. And so that's the end of the talk. And I'm looking forward to hearing from you. You are welcome to contact me if this talk resonated with you and you want to know more, or if you come to the actual Café con Leche on April 12th, or even if April 12th already passed and you happen to find this video on YouTube on the Lathisms page. So once again, thank you to the organizers for inviting me, and I hope you enjoyed the talk.